Hey everybody, so this video is all about describing what is a vector. We're going to talk about vector quantities this year and how to break them down into their components and figure out what resultants are. We'll talk about what those are, and hopefully this video will help you get squared away with some of that. To start with, what defines a vector? So a vector is something that represents a quantity that's both magnitude and direction. Magnitude being how much and direction being which way. So I want to make sure we're kind of clear on those two things. It can be illustrated with an arrow, which means this would be a vector. The length of the arrow indicates the magnitude. The direction it is pointing represents the direction. Some examples of vector quantities include velocity, displacement, acceleration, and force are some of the things we're going to get into this year that will deal with that. So, quick example, if we have a vector going this way at 1 meter per second, our velocity is to the right at 1 meter per second. If we were to draw basically double that, it would be 2 meters per second. Or if we had something going 2 meters per second the other way, we would draw it like this. But again, where the length indicates to you how much there is of that quantity, whatever it is, and the arrow pointing in the direction it's going. We're eventually deal with things where we have maybe a force of what's called 5 newtons acting this way, and a force this way of maybe 2 newtons, and then a force this way of maybe 4 newtons. And then trying to figure out, well, what's going to happen to this thing if these are all the things acting on it at one point in time. So we can do some certain things with vectors. We can go through some basic math principles. We can add, subtract, multiply, and divide. So for instance, if we have a 1 newton vector to the right, and we have a 2 newton vector to the right, we're going to add together. We end up with a total of 3 newtons, or 3, whatever the quantity is, all right, to the right. Or, for instance, if we had a 1 newton vector, a 1 vector to the right, plus a 2 vector to the left, the sum of those two would be 1 to the left, because the 1 to the right is canceled out by the double vector going to the other direction, so we end up with that 1 vector to the left. So how can we deal with vectors on different axes? Well, that's where we end up with this thing called head-to-tail addition, otherwise known as the parallelogram rule. So how we add components, the components being the individual vectors, to get the resultant, which is the sum of those, we will go through a process like this. So we have, say, a 2 vector straight up and a 4 vector straight to the right. The sum of those two, again, we're going to do head to tail. So what that means is we're going to take the tail of this 2 vector and draw it from the end of the 4 vector. So we'll just recreate it over here. We can also take the 4 vector and draw it from the end of the 2. So there's our 4. Get rid of that. And 2. And those should intersect in the same point. And you see here, now we have a parallelogram. In this case, because we have our right angles, our parallelogram is a nice little rectangle. But what that reveals to us is the key factor is this right here. That vector going in that direction is the one that's going to be the actual either direction of motion of the object or the force that's applied. If we were to replace the 4 newton vector here, we would replace this one and this one, it would equal this one right here. So this right here is the sum of those two. So we can take advantage of some properties of triangles to determine that. So the Pythagorean Theorem is great for that. So for instance, if we had a 4 this way and a 3 straight up, okay, we do our head to tail method. So let's draw the 4 newton in here and the 3 in here, and with that point right there, okay? And then we draw in our resultant, which goes from our starting point to where the two the two components intersect. And how do we figure out the length of that? Well, our Pythagorean theorem is a squared plus b squared equals c squared. We have one side of our triangle here, it's a length of 4. The other side of our triangle is a length of 3, and that all equals c squared. So 4 squared is 16, plus 3 squared is 9. That would be 25 equals c squared, so c equals 5. So if we have 3 up, 4 to the right, the resultant of that is this 5 vector going up and to the right in that direction right there. When we get into some further details, it should hopefully be even more clear as to what that means. So what we can also do is take that 5 Newton vector, say that's our 5 vector, or whatever it is, 5 meters per second, 5 newtons, whatever. We can break it back down into its 2 components, or as many components as we wanted to. This is going to work well for us with projectiles, because what we're really going to care about is that x-axis and that y-axis. What are the 2 parts of the vector that do that? So we're going to take advantage of the fact we know we want a vector going to the right, straight to the right. So we're going to take this 5 Newton vector and do the reverse of our parallelogram rule. We're going to go parallel to the opposite axis, go straight down to result in our 90-degree angle here. We're also going to go straight across, and we get our right angle again. Where these intersect, here and here, these are the same 2 components we started with in the previous one. So basically we're just going backwards from what we started with. So we're taking advantage of the fact that this is a 5 Newton, 5 vector, and we know there are 2 sides to that right triangle. Short side's gonna be 3, long side's gonna be 4. Kind of just based on undoing what we've done in the previous step. So there, we can do different angles. So we want to take advantage of what the trig functions are. For those of you that haven't seen or heard of the trig functions before, don't worry about it. I'm going to kind of go through those right now. These trig functions are going to help us figure this out for right triangles, because right triangles are pretty much ratioed to one another. If this one side is one length, if an angle is something, the other side has to be a certain length because of that angle and because it's a triangle. So if we have our base triangle here, okay, the sine function is based off, so you'll see that looks like sine of the angle. We're going to call the angle theta, and this is going to be our angle the whole time. The sine of the angle is going to be the opposite side, which is going to be this one over here, over the hypotenuse, which is this one right here. Okay. That's always going to be in a set ratio based on the angle because of how right triangles work. And that sine of the angle is some ratio, is a number basically that's programmed into your calculator because it's part of a functionality. It's part of a function defined. So this is some number. The nice thing there is it's going to allow us to figure out, if we know the hypotenuse or the opposite side, to figure out the missing one based off that. Then the cosine of the angle is the adjacent side over the hypotenuse. So let's get rid of this. The adjacent side is going to be this one. There's the adjacent side. And it's going to work the exact same way. The cosine of whatever number this is for the angle is going to equal some number, and that's going to equal to the adjacent side over the hypotenuse. Our third trig function is the tangent of the angle. And again, tangent of the angle is just some number that's kind of part of a huge table. it's the opposite side over the adjacent side. So that one is not going to involve the hypotenuse at all. It's only going to involve this opposite side over here. So we can get rid of the hypotenuse for that one. Don't need it. It's just the ratio of the opposite side to the adjacent side. And again, based on the angle, it's always going to be in that same ratio because of the limits of right triangles. So we need that to get components for some velocity. So let's say that we measured the speed of something to be 20 meters per second. And that was at an angle of 15 degrees to the horizontal. We want to know what are Vx and what is Vy. Because those are the two things based on what we see in projectile motion that really matter. Like how fast is going up is going to determine how long it stays in the air, and Vx is going to determine how fast it's going to go forward. So what we really want to know is this Vx. We also want to know this Vy. So you can see here, kind of drew these in, where we have our little triangle here, our little parallelogram, where we have this 15-degree angle and a 20 meter per second velocity, and we have our two components, Vx and Vy. This side over here is Vy, and this side down here is our Vx. So we can see we have our little triangle where this middle section is that length of 20. So how do we figure this out? Well, sine of our angle is equal to opposite, which is going to be Vy. Our angle is this right here. Opposite's going to be Vy right over here, over the hypotenuse, which is going to be the velocity, the object, which is 20 meters per second. Cosine of our angle is going to be the adjacent side, so that's going to be our Vx over the hypotenuse, which is the velocity of the object. How does this help me? Well, this helps me because we can quickly flip this and make this into, Vy is equal to V times the sine of theta, and Vx is V times the cosine of theta. And from there we can just plug our values in. 20 times the sine of 15 degrees, and this is 20 times the cosine of 15 degrees. And 20 times the sine of 15 degrees is 5.2 meters per second, and 20 times the cosine of 15 degrees is 19.3 meters per second. So this makes sense. If you're shooting an angle of 15 degrees, that's pretty close to horizontal. So most of your velocity should be in the vertical direction. And you're really not going to go very high in the vertical direction. Most of your velocity should be in the horizontal direction. You're really not going to go very high in terms of the vertical direction. So you're not going to spend a lot of time in the air, but you are going to travel pretty quickly across the ground in the horizontal direction. So hopefully this helps you figure some of the things out in terms of breaking breaking resultant velocities into their two components, which are what are going to help us figure out things in terms of projectile motion.